The Pacific Ocean. Hundreds of feet below the surface, a submarine has been silently patrolling for months. Inside the control room, officers monitor dozens of instruments while the vessel glides through complete darkness. Everything appears normal, but a hidden problem is growing. Fuel reserves are running low. The nearest naval base is thousands of miles away, and a submarine cannot simply stop in the middle of the ocean. Without fuel, it would gradually lose its ability to move, generate power, and sustain critical systems. The commander faces a difficult decision. The submarine must refuel, but that means surfacing. And surfacing means risking detection by satellites, radar systems, aircraft, or enemy warships. Hours later, a supply vessel emerges on the horizon. Massive waves crash against both vessels as sailors struggle to connect heavy fuel hoses between two moving ships. One mistake, one large wave, and the steel giants could collide. Today, you'll discover how submarines are refueled, why it's one of the most dangerous operations in naval warfare, and how modern nuclear submarines changed everything. Imagine standing inside a submarine, hundreds of feet below the ocean surface. An officer suddenly announces, "Fuel reserves are nearly depleted." Normally, when a ship burns fuel, it becomes lighter. As tanks empty, the vessel gradually rises higher in the water. But something strange happens with submarines. Even as fuel disappears, the submarine remains perfectly balanced. It neither sinks nor rises. How is that possible? The answer lies in a brilliant engineering trick. Unlike cars, many diesel-electric submarines store fuel in tanks located outside the pressure hull. These tanks are connected directly to the ocean through special valves. At first, that sounds insane. Why would engineers intentionally allow seawater into fuel tanks? The answer is pressure. At great depths, the ocean exerts enormous force on every surface. An empty fuel tank would be crushed like a soda can. To prevent collapse, seawater enters the tank as fuel is consumed. The pressure remains balanced, the tank survives, and the submarine remains operational. If seawater enters the tanks, why doesn't it contaminate the fuel? The answer comes from simple physics. Think about oil floating on water. The two liquids don't mix because they have different densities. Diesel fuel is lighter than seawater. As a result, the fuel naturally rises to the top of the tank while seawater settles beneath it. As engines consume fuel from the upper section, seawater gradually fills the empty space below. The water acts like a giant natural piston, constantly pushing the remaining fuel upward. This clever system solves another major problem: weight balance. If the submarine lost hundreds of tons of mass as fuel burned away, buoyancy would force it towards the surface. That would make stealth operations impossible. Instead, every gallon of fuel consumed is effectively replaced by seawater. The submarine's weight remains almost unchanged. But this ingenious system creates another challenge: contamination. Over time, sludge forms where seawater and fuel meet. If this mixture reaches the engines, it can cause serious damage. To prevent that, fuel passes through powerful centrifugal separators that remove water and impurities before it reaches the engines. Everything is designed around one goal: remaining hidden. Deep underwater, diesel engines are completely shut down. The submarine relies on batteries, moving silently through the darkness like a giant underwater electric vehicle. But batteries don't last forever. Eventually, they must be recharged. To do this, the submarine raises a snorkel above the water surface. Fresh air is drawn into the diesel engines, which power generators and recharge the batteries. However, the snorkel creates a visible signature: foam, wake patterns, radar reflections. Every minute spent snorkeling increases the risk of detection. And while snorkeling recharges batteries, it cannot refuel empty fuel tanks. When fuel levels become critically low, the submarine must perform its most dangerous operation: refueling. Movies often show submarines refueling from giant tankers in the middle of stormy oceans. Reality is very different. Attempting to transfer fuel between two large vessels in rough seas is extremely dangerous. A single wave can push thousands of tons of steel into collision. Even worse, two stationary ships are easy to detect from space. Modern military satellites constantly scan the oceans. A submarine sitting beside a tanker becomes an obvious target. That's why refueling usually occurs at secure naval bases or carefully concealed supply locations. Some are hidden in remote fjords. Others are sheltered among isolated islands. The submarine arrives under cover of darkness. A support vessel quietly approaches. Sailors drag heavy fuel hoses across wet decks while both vessels move with the waves. Every second counts. Once the transfer is complete, the submarine immediately returns to deeper water. What happens if danger appears during refueling? The answer is speed. Modern naval refueling systems include emergency breakaway couplings. If the submarine must dive immediately, automated mechanisms disconnect the fuel lines within seconds. Valves instantly seal both ends of the hose. Fuel leakage is prevented. The hose falls away, hatches slam shut. The submarine dives. Meanwhile, the support vessel quickly changes course and leaves the area. This constant risk of detection pushed engineers to search for a completely different solution, a solution that would eliminate fuel shortages entirely. The answer arrived in the middle of the 20th century: nuclear power. Nuclear submarines changed naval warfare forever. Engineers removed massive diesel engines and fuel tanks. In their place, they installed compact nuclear reactors. The difference was revolutionary. Imagine a train that could travel around the world for decades without refueling. That's essentially what happened with nuclear submarines. Instead of relying on field deliveries, they generate energy through nuclear fission. The reactor produces enormous amounts of heat. That heat creates steam. The steam spins turbines. The turbines drive propellers and generate electricity. Suddenly, submarines no longer need fuel tankers. They no longer need to surface for fuel. They can remain hidden underwater for months at a time. The limiting factor is no longer fuel, it's the crew. Living underwater for months presents another challenge. How do sailors breathe, and where does fresh water come from? Nuclear submarines use powerful desalination systems that convert seawater into fresh water. The reactor provides all the energy needed: water for drinking, cooking, showers, laundry, everything. Oxygen is generated through electrolysis. Electricity splits water molecules into hydrogen and oxygen. The oxygen is released into the submarine's atmosphere. The crew continues breathing normally. Hydrogen, however, creates a serious safety risk. Rather than venting it overboard and revealing the submarine's location, special systems safely process and remove it. Despite these technologies, life aboard a submarine remains challenging. The air contains traces of machinery, lubricants, chemicals, and the presence of hundreds of sailors living in a confined space. After months underwater, the smell becomes unforgettable. A nuclear submarine may have enough energy for decades, but humans don't. Eventually, food supplies run low, fresh produce disappears. Fatigue accumulates, psychological stress increases, months without sunlight begin to affect the crew. Even the most advanced submarine cannot overcome basic human biology. At some point, the mission must end. The vessel heads home. And that's when another extraordinary operation begins: replacing the reactor fuel. Inside a secure shipyard, the submarine enters a massive dry dock. Water is drained away. The vessel rests on enormous support structures. Around the reactor compartment, engineers construct protective barriers made from steel and lead. The crew leaves the submarine. Specialized nuclear technicians take over. The reactor is shut down and cooled. Then comes one of the most delicate procedures in engineering: removing the spent nuclear fuel. Heavy cranes carefully extract fuel assemblies and lower them into deep pools of water. At this moment, something incredible appears: a mysterious blue glow. Known as Cherenkov radiation, it occurs when charged particles move through water faster than light can travel through that medium. The result is an eerie blue light that seems almost supernatural. Replacing nuclear fuel is a process that can take months, but once complete, the submarine is reborn. Its reactor begins operating once again. Turbines spin, electricity flows. The vessel regains its near-limitless endurance. Some modern nuclear submarines are designed with reactor cores that can last over 30 years without replacement. From the day they're launched until the day they're retired, they may never need refueling at all. And that's what makes submarines some of the most remarkable machines ever built. Whether powered by diesel fuel or the atom itself, every submarine represents a masterpiece of engineering hidden beneath the world's oceans.